Welcome to the Knowledge Crafts seminar. As you know, our theme for this week is What is a Knowledge Graph? Today, we are very pleased to have with us Dr. Chaitanya Baru, who is currently a senior science advisor at the National Science Foundation. Throughout his career, Dr. Baru has been involved in working with big data, be it creating it, harnessing it, or benchmarking it. He's currently involved in the Convergence Accelerator program at the National Science Foundation, as part of which they are funding several initiatives in the area of knowledge graphs. Today, we will hear from him. What are knowledge graphs and why do we need them? Over to you, Chaitanya.
Great. Thanks very much, Vinay. So I'm very happy to be here. I prepared this set of slides just for this occasion, so it'll be kind of like the first time I'll be going through it, but hopefully I should be able to get through all of them. And the point of these slides is I'm trying to, in a way, tell you the story of actually one of the what we call tracks in the Convergence Accelerator that was just mentioned at the National Science Foundation. And this track is on something called the Open Knowledge Network, which is really about creating knowledge graphs in a variety of different scientific domains. So I just want to take it as a journey, starting with what are these things that we are talking about, and why do we think we need them? So let's see. There we go. So if I start at the very beginning, I think it will, Vinay sort of alluded to this, but from my own background, I'm a database guy. I'm a computer scientist who worked in database systems. And so that's an area where we are basically concerned with this whole issue of managing data and how do you represent it in a powerful enough way. How do you store it efficiently? How do you process it and query it? I think Vinay also mentioned some of the benchmarking works I've been involved in. So if you go back all the way to the early days when, in a sense, the real sort of application-oriented business computing started, people were worrying about how do we represent the data and how do we store them in the system so we can do something useful with them. And I'm just showing this to show that if you think about connecting in a graphical way, the objects that we care about in any application, at some very 100,000-foot level, that was, of course, the original way people were thinking about this, right? So here on the right side are examples of, we have professors, we have curriculum, courses are taught by professors, a set of courses make up what is a curriculum, and then for each course, there's some offerings, there are these one-to-many relationships. And then it turns out that maybe actually a course can be in more than one curriculum. So we have to do many-to-many relationships. And these are all the kind of things that people realized early in the day and try to come up with models for dealing with them, which kind of look like nodes and edges. But really what they were talking about is how does all of this get stored physically on disk in an efficient way? And there's actually a lot of analogies between this diagram, these kinds of diagrams, and the physical way in which the data was actually stored in the system. So in some sense, not too much transparency between how we logically represented it and how we physically represented it. But soon after, mid-70s, was the advent of this entity relationship diagram, ER models that you might have heard about. In fact, in the very first issue of a very well-known, now respected journal, ACM Transactions on Database Systems, was Peter Chen's paper on entity relationship model, and that's the diagram at the bottom. That's a little bit more conceptual. It's still talking about professors, courses, curriculums, and offerings, but that doesn't necessarily have to map to physical things. We know how to, there are many different ways in which you could have mapped them onto storage. So that's just to say that these kinds of linked models, if you want to think of them as graphs, in a way have been with us from the beginning, but something has been changing along the way. As I said, the focus of a lot of these things were really much more on storage and processing of the things. And the focusing of the ER diagram was just on the conceptual modeling of trying to capture what there is in the real world application. I'm fast forwarding all the way to the 1990s when we started talking about object-oriented models, and only to show that by the time we came to object-oriented approaches, we realized that actually there are many different kinds of relationships between these objects. So the many different kinds of edges that connect these circles together. It could be class hierarchies, that something is a type of something. So, a class inherits from other classes. It could be composition, that a class is a set of classes formed together to create another class, and so on and so forth. There were also the earlier one-to-many and many-to-many kinds of relationships, but much more richer model started from more on the software modeling side, but similar concepts were also adopted in modeling data. Again, more at the conceptual level, eventually had to be mapped to how do you want to store it. And now I'm fast forwarding 30 years from there to now. And what's going on now, I think when I mentioned big data. So along the way, what happened was our ability to produce enormous amounts of data, thanks to all the computing power that we generated. And also along the way, we invented the internet and the web, which just led to a proliferation of information that was all in some sense connected just because they were all connected through nodes on the internet. But that was really the advent of a variety of different data coming online. There's both the unstructured data that you see on the web, but a lot of websites behind the scenes have sort of the deep web, which is maybe coming from structured databases. There's a lot of heterogeneous data here because it's not that this was done by design, right? Anyone can add a node into the internet. It just happens to have whatever data it has. Maybe some nodes have lots of images, others have text, and so on and so forth. There could be information about you as an individual and all the different things that you're connected to, whether it's your images, it's your other information from your, let's say, CV. It could be other kinds of information that might be, let's say, are related to now that we're in the pandemic time, disease-related information and all the things that go with that. It could be geographic location information and so on. So it's a very broad range of information that we have to deal with. And the need that we have in the case of something like the web is how do we create ability to search in some reasonable way all of this data, what kind of knowledge representation schemes do we want to have, and what querying schemes. And so we'll touch upon, I won't go into the details of any of this. As I said, the point of this is to get you to the story of the kind of projects we're doing. But there are schemes like SPARQL query language, OWL as the modeling ontology, web language, and there's a lot of computational power that actually enables us to do this. So a lot of this, in fact, almost all of it, couldn't really have been done if we didn't also have the computing power behind the scenes to do it. So this is where we are. And the way we are trying to get our hands around how do we manage query and do something useful and reasonable with this information, with this data, is what brings us to these notions of the semantic web. So instead of saying, well, it's all just a bunch of data that's sitting out there, are there ways to represent what the meanings are, what are the relationships among these data sets? If there a lot of the data on the web is open, how are these data sets linked, and can we use that linked structure to then provide actually more intelligent search interfaces and more intelligent maybe inferencing with the data and so on. So here, a couple of diagrams that show when people talk about semantic web, they're talking about the linked structure of data on the web, but they're also talking about maybe standardized vocabularies so that we know what is the information we are looking at and we understand some of those relationships. Semantic web does include the notion of ontologies, and we'll talk a little bit more about that. And basically, what are the conceptual structures, once again, of how this information is related to each other. The other term that you will hear on the web is, of course, linked open data. And again, there the notion is, the web is full of data that's implemented using whatever standard internet web protocols. A lot of it is open. Some of it may actually be linked using schemes such as the Resource Description Framework, RDF, that we'll look at just in a bit. And that actually forms another structure. Now here you're not seeing, when we talk about linked open data, we're not necessarily seeing that we need to have a reasoning system, a rule system, ontology, and so on. But these are both related concepts and sort of variations on the theme. And that's something to keep in mind as you go through this area of knowledge graphs and knowledge networks. There are, one might think of as, subtle variations in the representation and the capabilities, but those do exist. And in some cases, you have big communities that are behind one way of looking at things versus the other. I also want to mention that this notion of connecting the data together, making the data more easy to search and discover, and then forming linkages is very current, and it's one of the most active areas going on now, which is why even at NSF, we're interested in having this track on that. And here's an example of something that's current and ongoing. Data.world is actually an organization. It's a company that provides the ability for organizations to, starting with metadata, to, in some sense, have rich metadata, that is, show all the structure and relationships in the metadata about data sets themselves, but also represent the data in using a knowledge graph method. And we'll talk a little bit more then about what knowledge graphs are. But if you go to the data.world site, they'll say that they're powered by a knowledge graph, automatically builds connected web of data and insights you can explore with relationships. You can get recommendations of related assets. So these are all concepts that come together, right? So once you have things that you want, that you can represent with connections to other things, then you can imagine that operations like search could be enhanced, or recommendation systems could be enhanced, because if you land up at a node, you can say, well, now that you're at this node, there are these other nodes connected to it, and are you interested in looking at that, and so on. So these are active, ongoing enterprises right now to create these kinds of knowledge graphs. So let's just say, again, by way of very high-level introduction, so when we say knowledge graphs, what are we talking about representing in those? So I started a level saying there can be a very abstract, high-level definition of what knowledge itself is, right? If you look up your standard references, there are sort of almost philosophical ways of thinking about knowledge. We are not certainly talking about that kind of, at that level of abstraction. You could talk about scientific knowledge, which is a method of inquiry based on gathering observable, measurable evidence, reasoning with that. The method consists of collecting data through observations and experimentations and formulating and testing hypotheses. Now that starts coming closer to what we might be interested in, because we are interested in data. We are interested in the fact that people are collecting data. These data may very well be science observations. And we want to start making relationships among observed data. Of course, observed data doesn't have to be just science. Commercial data is all, to some extent, observed data, one can argue. And the definition of, for scientific knowledge to be useful says it should be, the system should apparently be dynamic and self-organizing, because that's what science is. Science is extremely dynamic. Again, if you think about the pandemic, what did we know about COVID-19 a year ago, and what do we know now? What did we know about how to recover from it then versus now? not just societal information, but the entire scientific knowledge has evolved just in a period of 1 year. So it's extremely dynamic. And so what are the structures you create? And then later on, I'll mention this is actually going to be one of the challenges. And how do we really keep such a highly dynamic system self-consistent and functional and usable as it's changing all the time? The knowledge must constitute some representation of the outside world. It's the observed phenomena. That's what we are interested in. And then there must be some way to exist. There should exist some way that you can get to this quickly. In other words, how can we process this through like query processing approaches or other analytics we want to do? So like I say, in knowledge graphs, it's not this so-called epistemological sense of philosophical knowledge that we care about. It's actually a very data-driven approach that we care about. We are saying we have a bunch of data, and how do I sort of represent that using this knowledge graph mechanisms? And the data is about real-world entities. And this graph of the entities and their relationships is the start of the knowledge graph. And I know that in the introductory lecture, I think that Professor Chowdhury gave you, he did talk about this as the model for knowledge graphs. And this is just a quick reference. Back in 2016, there was this paper defining a variety of different definitions for knowledge graphs, mainly containing real world entities, their relationships, and so on. And the paper shows a diagram that looks like this. The architecture of a knowledge graph, of course, has the knowledge base itself. That's the data itself. But once again, the term ontology comes here. And we'll come back to that. Do these data have to fit some kind of a known structure or known conceptual hierarchies and so on? But it also shows a reasoning engine. So basically the ability to query and do something more with the data. And that's defined as a knowledge graph, all of that together. So since the term ontology has come up here, let's look at that. And I think a functional definition for us is basically to think about ontologies as a more formal representation of things that we might be able to describe in a natural language. So if there is a set of concepts, a set of observations that may be science data, and we can talk about what they are and how they are related to each other, that can be the start of deriving what your ontology looks like. So the figure in the middle says that the ontology, in some sense, you can think of it as serving two purposes. It helps you express the content, so it helps formalize the content, helps express the structure, maybe class hierarchies, maybe relationships, what is related to what causes what entity is located where, which entity is derived from what other entity, or which entity influences another, could all be things that help you define what the structure of it is and basically the content of the data. On the other side, it's also being used to define the domain itself, and it may have other aspects to it related to the governance of that information, how reasoning should be done with it, and what's the context in which this is being presented. So some of it may be the metadata associated with it. So there's both sides to it. There's sort of the content side of representation of the data, and there's the domain side of describing what it's about. And here is an example of what an ontology could look like. And interestingly enough, it's kind of back to our 1970s diagram of kind of professors and universities and courses. In this case, it's universities, have schools, have research groups, universities maybe employ people, and they have researchers, and the researcher is a kind of person. Researchers have publications, and books and articles are kinds of publications, and so on. So structures of this kind is what ontologies help us define. And they're useful because in a way, it's like saying, we remember we started by saying that the web has all these unstructured data sitting there. And from there, we are slowly coming back to saying, well, there should be some structure on top of it. So that's sort of the interesting play here is we're starting with data and we are saying, well, we need to be able to put some structure, i.e. ontologies on that. But where do they come from? How do we define these ontologies? So I think we can say that there is two ways of thinking about ontologies. One is just designing them. You can get a bunch of folks sit around a table and say, yeah, what does a university look like? And come up with this diagram. It has this, it has that, there's these components and so on. And that happens again in science a lot. I've certainly been in rooms full of let's say seismologists, geoscientists, who will sit and try to define what is an earthquake from a scientific point of view, right? What is an earthquake? It's a discontinuity in the landform, and also, and go on and on. So you could just sit around and define from what you know what the ontology should be. Another way to do it is to derive it from a lot of the unstructured data that we have. A lot of it could be text, and we can look at things described in the text. So here's a piece of text that's really talking about drugs and the actions that were performed using drugs and the quantities that were used. So you might need to have some system that will at least tell you this is a drug and that's an action that was done with it. And these things, these numbers are quantities. But then you actually extract all of these and find the relationships between them. And that's actually another way of developing ontologies. So both are valid. Both have their issues. In a sense, the second approach of deriving it from unstructured sources, I think still requires some kind of checking, at least in science use cases. You still want to have maybe experts look at it, but it can actually be very powerful because you can do it much more quickly. And not all of it might require to be checked. It kind of depends on what the applications are. And hopefully some of what I say later will reveal some of that. Okay, but then going back to the entities that we want to have in these knowledge graphs, where do they come from? So by now, as we said, we have lots of structured data in the world. We also have lots of unstructured data. So structured data are your typical, you can think of it as relational databases, row column kinds of things. They occur in corporate databases. In fact, many scientific databases have these kinds of structures, and they do have schemas. And you can derive your entities from those tables. You can derive your ontologies from those schemas, at least part of it. But there's also a majority of data, a vast majority of data still exists in unstructured form, whether it's text, videos, signals of all sorts. And we want to be able to extract, again, as we've seen so far, structure from all of these things. And one of the models that has emerged, as you've heard also in your previous lectures, is the node edge model. And RDF is one of those models that basically is a triple model that is a subject, predicate, object connection. Professor Chaudhary teaches knowledge graphs. And that becomes a very simple but very powerful way of representing this information. Note that at this point, we are not really worrying about efficiency of storage or efficiency of processing and so on. I think later on what we are going to find is that there is sufficient, more or less, sufficient computing power to be able to do some of these pretty efficiently, though I think it still continues to be a computer science problem of how to build truly highly scalable, highly efficient systems for extremely large knowledge graphs. So as we said before, we are trying to once again bring back structure onto these unstructured things. If we have a simple model like this, that's just a subject predicate object model, how do I express something more sophisticated than just the simple triple model? So once again, we go back to this notion of developing schemas, which are ontologies of some sense, basically showing you some basic relationships among objects, but doing it in a, I would say, a much more sort of a loose way, than you might do when you try to sit and define a strict relational database schema with all the integrity constraints that go with it with the database. Okay, so schema definitions and this whole movement of schema.org has become extremely well. It's well used. You can say it's become extremely popular. If you go to schema.org site, it says here that over 10 million sites on the web use schema.org to mark up their web pages and email messages, right? So if you if you do a search on Google or even Google Maps and you're looking for a store, it shows you the store hours. It might even show you the when it's the most busy and so on. That's all actually structured data because somebody decided to mark it up in schema.org markup and put it on the web. And then these engines that know how to process RDF are able to interpret it. The reason that happened is because there are so many stores, millions of stores that have information on the web, and all the stores found it useful to be able to do that. So this is basically one way in which a schema evolves, is that there's just a whole lot of people, there's a whole lot of data out there that is of very similar kind. And the people who are putting out that kind of data are willing to mark up their thing because there's some benefit to it. In this case, it's the search engine is showing their data in a much better way than if they had not marked it up. So applications from Google, Microsoft, Pinterest, et cetera, are all using these kinds of capabilities. Schema.org itself has this very basic schema. Let's see, I need to move something on my screen. There we go. Has this very basic schema of basically things, and things are related with action. Things could be creative work, could be event, could be intangible, et cetera, and then there's data types, and there's a type hierarchy, and there are these very basic kinds of types. So it's a very simple basic model to begin with, and a model like this can then be extended for new applications. So in this case, suddenly we realize that we need the ability to describe special announcements. So we can then attach it in this hierarchy. So we can, under creative work, which is under thing, we can say there is something called special announcements, and now all of a sudden everyone can start tagging with that, and any RDF processing engine will then see it. So it's highly extensible in that sense. And here's a concrete example of what happened during COVID-19 about a year or so ago, and I was actually involved in this working with the Google folks because they were trying to get all of government agencies to use the schema.org tagging so that government websites could be tagged with the right kind of COVID-19 information, and people could find that information more quickly. So March 16th of 2020, seems like ages ago, they announced that they're going to make some extensions to schema.org to accommodate COVID-19 information. So special announcements was part of that. And this next, there's a blog associated with schema.org that shows you all the changes and the new releases and so on. So version 7.0 of schema.org, which was released March 17th of 2020, had all of these changes. And one of these, it says here, is introduced a virtual location type to support description of events whose location is online, right? So all of a sudden they had the need where people would go to a event site and would need to be informed that this event actually has now become virtual. So you don't go to this physically, there are virtual coordinates for this. How do I express that? So this was an extension to support that. So it added the event attendance mode to clarify whether the attendance mode of an event is online, offline, or mixed. And of course, now we are all used to hybrid classrooms or all online classes and so on. But none of these ideas existed a year ago, right? So I just want to put this out to show you that one advantage of this kind of approach is you can very dynamically change things. And then here's a more detailed markup, a description of, this is really the ontologies, the schema.org extensions, which then people can use to mark up their sites. There is disease prevention information, disease spread statistics, getting tested information, and so on and so forth. So this can be very dynamic and very flexible. Usually what happens is you want to get some kind of a community consensus on what are the right kind of things to represent. Here was a case where this was done extremely rapidly. I think within a couple of weeks from the idea starting, we got a bunch of folks to agree on this. It included folks doing schema.org, some folks from private sector dealing with medical information, people at places like HHS, Health and Human Services in the federal government, and CDC, all looking at it very quickly and saying, okay, yep, this makes sense, let's do it, okay? Now, once you have those kinds of triples and you do have some schemas that you can use, again, I'm not going into the details of this. I think you have lectures coming up on more detailed technical descriptions of SPARQL processing and distributed SPARQL and so on. But this is just to say that there are query languages that one can use and which look pretty reasonable. If you look at the syntax here, we are saying select the name and email for persons, right? That's what this query is. And so apparently there is an ontology. In this case, it's actually a well-known ontology called Friends of a Friend, which is published and available. So if you end up using that to describe a person, then automatically a whole lot of tools will recognize what you're saying. Using the FOF ontology, we can say, all persons, I want to get their name and email. Here's the second one is another example that says, we are imagining that there is a ontology that talks about countries being in continents and that countries have capitals. And therefore I can ask a query that says, give me the capitals of all countries that are in Africa, right? So I just want to show this as to say, we are coming eventually, having created the structure of the schema on top of RDF. Therefore, we now actually have a query language that we can use to process it. If we are, some of what I'll allude to later on in our projects is there are extensions needed. This, as you add more, let's call it more variety of data into the system, the current capabilities of SPARQL itself may not be enough. In fact, there is something called GeoSPARQL, which extends SPARQL with geospatial and spatial kinds of operators. So those will keep happening. It's the natural way of evolving these things. So why do we want these knowledge graphs? What is the thing that's pushing us to have these and to use these? And on the sort of open web or in the commercial sector, there are applications like search, Google, Bing, Maps applications, all use these knowledge graphs because they are having, they do have these kind of schema.org kind of structures behind the scenes. So when you type something like Galileo, when they recognize that you're talking about this, first there's a question of recognizing the term, but then they say, they might give you a set of options, one of which is Galileo, the scientist and the artist. And if you click on it, they will recognize that this is actually a person who is an artist, scientist, who has a lot of works associated with him or her. And the way the information is represented is actually in a way the display itself is induced by the knowledge graph. Same thing that goes with catalogs. If I'm searching for something in a shopping catalog, there are things like, well, people who search for this also search for that. Well, that all happens because this information is represented behind the scenes, and the system is actually using that information to even control how it is displayed to you on the screen. So that's a very powerful capability. Similarly, there are smart assistants like Siri, etc., that are also using knowledge graphs to give you sensible and hopefully slightly more complete responses back. Why do we care about it in science applications? Well, even in the scientific applications, we do care about search and discovery and data exploration. And this is because of a number of reasons, one of which is there is explosion of data in science as well. If you're a biologist or a geoscientist or even social scientist, there's tons more data out there than there used to be, a few years ago, 10 years ago, 20 years ago. And we need more sophisticated capabilities to be able to search for these data. It's no longer the case like where a scientist says, oh, I'm looking for this kind of ecological data, and I know exactly where to go get it. You don't anymore because there are so many sources. Another huge requirement, and I think we're just at the beginning of this, is basically, you might loosely call it integration, pulling together very heterogeneous data. So science itself is moving in a direction, whether it's in medicine or climate change or any other field you can think about, transportation infrastructure. It's no longer a single mode of data, a single modality that you're looking at. You're looking at data that comes from a variety of sources and variety of disciplines even. And so this is very heterogeneous data, and we need to have some way that we should be able to link all of those together rather than making the scientist fight through it from sort of basics each time. Having all of these data connected together in a knowledge graph kind of way also would enable analysis. So you can do some of the more intelligent things, just like recommendation engines can recommend things for you because they know the relationships. Science search can also do that for you. And there's also another extreme, rapidly growing area, which is connecting data with models. So increasingly, we're using machine learning models to derive results from data sets. And we want to be able to link these two together to say, for example, well, not only just this model was derived from that data set, but also to say things like a model like this could be used on data sets that look like that. Okay, and that's a knowledge graph kind of relationship mechanism that increasingly those kind of things will become important. So where do we get these from? So if when these people were building, let's say when the Googles and the Amazons, etc., are building these large knowledge graphs, you got to harvest those entities from somewhere to begin with. So one movement was, there's no shortcuts here. It turns out that you just have to go get them, right? So it turned out that there was this a project, and then ended up as an enterprise called Freebase, started in 2007, that actually harvested data from a number of existing sources and did all the hard work of putting it together. And coming up with the entity relationship and triple model representation of it, which was then acquired, in this case by Google, which then used it internally to essentially prime their search knowledge graphs, right? So there's now a Google knowledge graph with an API and so on. Similarly, 2012, Wikidata started as a way of collecting data and representing it in a way that it can actually be used, not just as text, but in this kind of knowledge graph approach. There was a talk in 2018, a couple of years ago, from Luna Dong at Amazon, talking about how Amazon went about building their knowledge graphs. And there are lots of similar stories for other companies as well. It's a combination of acquiring others who have done the hard work, or you just sit down and do all the work, okay? So when we look at all of that, we are thinking about it now from the science side, as I said, with all the explosion going on in science. And the point was, we said, well, we need to have a similar system also in science applications so that we can enable, like I said before, the search, the discovery, the integration for scientific data. So back in 2017, there was a workshop held among the federal government agencies, which resulted in this report called the Open Knowledge Network report, and which basically said that an open broad community effort to develop a national scale infrastructure is needed to make all of these data broadly accessible to a wide variety of stakeholders. As I say, as science gets more integrative, It's not that data produced by one community of scientists is being used only by that community of scientists. Increasingly, one community might produce some kind of data set, another completely different community wants to use it because of the kind of analysis they're doing. So like, if you're trying to say put together a transportation network, you might actually want to get a lot of socioeconomic data because you're concerned about the social, the economic disparities that might exist in neighborhoods. And you want to see how the transportation infrastructure is sort of gelling or not gelling with the fact of, where are the people living who actually need access to the transportation and so on. So typically you would think of these as two very different data sets. One is coming from the transportation engineering sector, the other is coming from socioeconomic data sets, census and things like this. So this infrastructure has the potential to really push forward discovery in a lot of areas. So I think we do think of this as being very essential infrastructure for the future. And then I'll now just quickly give you a sense of what we currently have 5 projects that are ongoing that are using this approach of creating knowledge graphs and knowledge networks in very different domains with very different objectives. So let me just describe them to you. But before that, sort of the punchline of it is to do these kinds of things actually does require a heterogeneous team, collaboration among both knowledge representation, knowledge graph, essentially computer science type experts on one hand, because they know what the capabilities of the system are, what the limitations are, and so on. And you need the domain experts, because the domain folks are really the ones who can help you with those ontologies and the relationships and what are the important relationships and so on. But you also realize that even in science, data can actually come from very different sources. They can actually come from highly curated scientific databases, which are known to be top quality, vetted, curated data, highly reliable, but they can also come from crowdsourcing, right? People observing things. This could happen in, let's say, ecology, where a lot of people do ecological observations, whether they're looking at birds or they're looking at fish or they're gone out fishing, and they'll come and report something about what they've seen, and that's crowdsourced data. At the same time, there are scientists collecting highly regulated data in the same domain. And also what we are finding is that this technology is so it's essential that there's also the need to educate the next generation of scientists in how do you actually use these kinds of tools, and how do you, well, even regardless of how powerful a tool might be, it does have its limitations. A knowledge graph would be only as good as the data it's built on, the kind of ingestion it might have done, the kinds of quality control. So to understand all of that may not be something that scientists would naturally learn in their own disciplines. They may learn some aspects of data, but not these kinds of things. So all of these are important things, is sort of the lesson to be learned. We are supporting these 5 projects through something called the Convergence Accelerator. So Convergence is this notion that multiple disciplines need to come together. Accelerator is the notion that these are projects that can be accelerated if you give them enough funding that in a couple of years they can make significant impact. So I just want to mention this, and you'll see why. I won't go through all the details, but this program at NSF, which is very different and unlike anything else that is at NSF, goes through this 3-step process. The first part is not important here, but we do go through an ideation phase to decide what are the areas in which we want to have projects. So as I mentioned, open knowledge networks is an area. That's how we came up with that area. But once we picked an area, we make projects go through a phase 1 and a phase 2. And these are very quick. Phase 1 is up to a year, and you can get up to $750,000, which is basically for you to bring together the multidisciplinary team and do the prototyping to understand what is it that we're going to build, how complex is it going to be, are we ready to go build it in phase 2. And phase 2 is you can get up to $5 million for 2 years, which is actually quite a bit of funding. But the idea there is to just run with it, and go forward and do what you thought, what you had planned to do in phase one. There is a curriculum. The reason I mentioned this is one of the things you do in phase one, all of the teams go through a curriculum. And I want to say a little bit about it because actually it turns out that this is important for something like developing knowledge graphs. Our curriculum includes, it includes user sort of modules or lessons on how do you do user discovery, or how do you figure out who your users are, using human-centered design, prototyping, making sure you understand what it means to prototype, what the different steps are. Remember that these teams are very heterogeneous. Not all of them are computer scientists. So people like computer scientists or even engineers might know what a prototype is because they might have built things, but not all sciences have the same notion of prototype, like a software prototype, like what a computer scientist might naturally be able to imagine. And team science. How do you work together in a team when you have a very diverse set of folks? There are also other modules, but these initial 4 things I want to say, I think we are realizing are actually very essential for developing things like, actually for developing the open knowledge network and for developing knowledge graphs, because it turns out that in building these things, you really do need to understand how is it going to be used. So you're not going to build this in abstraction, devoid of thinking about what the usage of this is going to be. It does turn out that you have to prototype these things because it can still be fuzzy for the user. You've got to be able to show them what you're doing, and then they might say, "Oh, that's the way you represented it, and this is how you're showing it to me. Actually, I don't like it. No, that's not how you're supposed to do it." And so you might have to go back and do it. And of course, team science, because when you bring together technical and people with the scientists, they're very different cultures, terminologies. People need to be able to work together. I think this also applies in corporate settings. If you have technology people building, there's always a customer to whom you're delivering it, and you got to be cognizant of that. So quickly, the Urban Flooding Project is basically creating a knowledge graph related to urban flooding. The diagram here shows on the right side, the map diagram shows that in an urban setting, there's actually a variety of siloed data sets that are all maintained by different folks. Could be different agencies, could be different actually companies. So there could be the electrical power grid data, there's the road networks data, there is public health information, and socioeconomic data, and so on and so forth. So all of these circles that are shown here are all essentially disconnected because they're completely different players who are all involved in putting those together. They're putting it together for their own purpose. And all of a sudden you come in with a problem like flooding and you say, well, that's going to impact everything. If there's a flood, it might bring down the power grid. It might block up the sewage system. It might cause public health hazards and so on and so forth. So you want to connect all of these networks together, actually all of these data together in some sort of a knowledge network in order to be able to answer these questions. So that's one challenge they have, linking together information in an urban multiplex. Another thing they're trying to do, which is unique in this project, is it's not just all data. In fact, a lot of flooding information is through models. You actually have models that will model for you, if there is so much rainfall in this geographic area, here's what the water level is going to be. So here's what the flood might look like. And it turns out there are, if not, well, at least thousands, if not tens of thousands of flood models for the US. Every region has its own model, okay? So every region has its own expertise. People in Florida might tell you that, oh, you're from California, you don't understand how water works here. No, we understand how to model the system here. And people from California may, same thing, you can imagine the state of Washington and so on and so forth. And all these models are producing outputs with varying levels of precision and so on. So all of that has to be put together in order to basically connect the observed data and the predicted data And so that's another aspect of it. And the final thing that these folks realized is it really depends who wants to consume it. And that was what we said earlier about user-centered design, is even in the knowledge graph, not everyone needs that knowledge served to them in the same way. So it depends. Are you just a private citizen and want to know, is the water going to get into my house, or is my street going to be flooded? Or are you somebody who's managing the power grid and want to know at what point do I need to shut off this part of the power grid, and so on and so forth. And because of that, even if the underlying knowledge graphs are the same, basically underlying data is the same, how you impart that to the end user is going to be different. So that's about this project. Some of these, I should say that some of these you can probably Google and find information on the web, but these teams are all actively working together. I just had a meeting with them today to build a more a good website where all of this information will be available together. So, watch the space. In the next 6 months or so, there should be a lot more information available online. Another one in a completely different area, this is biomedicine, is the SPOKE project for scalable precision medicine. I should have mentioned in the previous one that it's Professor Lilith Yagazarian from University of Cincinnati is the PI. For this one, it's Sergio Baranzini from UCSF. And as the graph here, as this diagram here shows, that they're actually putting together heterogeneous data. In this case, there are genes. This is human health, so there are human genes, there are diseases, and there's tissues where the diseases relate to and where the genes are expressed. And it's all the relationships between these things. And all these little circles around the big circle at the little circle at the bottom are all the independent databases that have been going on for many years and strongly collected data about immunology, oncology, and so on and so forth, the reactome, et cetera, that are all sitting in separate databases. And what they're trying to do is pull together all of that heterogeneous data into a knowledge graph to be able to then answer questions about disease interactions. One of their use cases is drug reuse. Can they discover through the knowledge graph that a given drug actually has some properties to it that may not have been known just because they found the connections. And I can't go into the details now, but they actually discovered some of the COVID-related connections with the genes before papers were published with lab experiments doing it. They just found it in the data. And they speculated that this might be a connection. And then there were other people published other papers showing that it indeed was a connection. They talk about meta nodes and meta edges, which is really just actually entity types and edge edge types, you can think of it. So basically, it's like it's a schema definition. And what they call meta is they're saying, well, there are different types of nodes. So each node is a kind of a meta object. And that our graph consists of not homogeneous set of nodes, but heterogeneous nodes that are drawn from a set of types. Similarly, the edges are all drawn from different set of types. And then there's a whole sort of query processing that can be done once you know the edge types, node types, and the connectivity. There's actually a bunch of references. I think the slides are already up there, so you should be able to see it. And some of they're very interesting papers. The first one is a good summary of sort of how the whole thing works from a knowledge graph point of view. The third project is, again, completely different. In this case, it's court records, legal court records from jurisdictions across the US. The problem here is all court data is actually public record. Now, once a case goes to court and is adjudicated in the court, whether it's settled out of court or actually litigated, etc., all of that documentation is public information, except right now they all sit in PDF files. And there's one website that you actually have to pay some money for each PDF page that you look at. So even though it's all public data, you pay for it just because they say, well, it takes us some effort to put it on. So what this team is trying to do is to take all of that data and just make it open. through a knowledge graph, right? So they're going to process all the PDF text and look for all of the entities. So entities in a text could be the name of the judge, the name of the court, the jurisdiction, what kind of case was it, who were the litigants, and so on and so forth. Right now, it's you can't even do some of the simplest queries you might imagine. No, just a random query. It's like judge so and so. How many cases of this type, let's say assault, did that judge try in their career? You can't ask that question. It's all there in the PDF documents, but it's not in the form that can be accessed and queried. So that's what these people are trying to do. They're very much focused on sort of the justice and equity issues here. One of the things in the process is they're looking at the PDF documents and inferring structure, essentially inferring semantics about what is that document about by looking at the physical structure of the document, which then gives them hints about, oh, the text up here is the name of the judge, and the text over there must be the name of the office, because all cases that are about such and such, they all look like this, right? And in the process, they're also actually developing ontologies. It turns out that there's never been an ontology developed for legal data. So things like events, that is, the disposition of a case. How does the case get settled? There's no ontology for it. They're seeing that there's actually a life cycle for cases. They actually go through different steps, and they may go back and go forward and so on. So they're developing all of the structure, knowledge, representation, ontologies, etc., for that kind of thing. This next project, the previous three, we think of them as sort of vertical projects, kind of in a computer science jargon, because they are about domains, right? The first one was about flooding, the second one was about biomedicine, and the third one was about court records. These next two projects, we think of them as kind of horizontals, in the sense that they're developing capabilities that anyone can use. So this project by Mike Caffarella, who is at Michigan and recently moved to MIT, is on developing essentially a knowledge graph programming system. I think of it, and I keep telling Mike that I think of it as it's like an IDE for knowledge graphs, right? So when you write Java programs, you don't start from scratch. You have an IDE from where you can borrow a lot of classes and just start putting it together. Similar idea, right now, knowledge graph development is kind of in the assembler stage, right? It's in the very handcrafted stage where everything has to start from scratch. And he's saying, well, let's raise this one level of abstraction and think of it as a programming environment. So how do you build data-driven software systems? In this case, actually knowledge graph-driven systems, where debugging of data quality is built into the programming environment. The concept of social knowledge networks is built in. That's actually an interesting and I think very powerful concept, because it turns out in the real world, when you're developing these knowledge networks, it goes back to our idea of team science and having teams doing it. It's not an individual's activity. It's not a single person who actually does it, because you need the experts, you need the technical experts and the domain experts. So it actually ends up being a teamwork activity and social in that sense. Plus, if you put a knowledge graph together about something, let's say transportation, there may be transportation experts, all over the country or in other parts who you might want to have an interaction with and say, I put this together, what does it look like? So if you look at things like Wikipedia and Wikidata, they are actually social systems, because anyone can go and edit, and there's a sort of a, not just a crowd aspect, but there's a sort of a social aspect to how the thing evolves. And that's basically the idea here. How do you provide a programming system that has those kinds of things that are naturally supported within the environment? And along with that also comes provenance. Provenance actually turns out to be a very central, essential aspect of these things, especially when you're talking about scientific data. You want to know, where did this piece of data come from? And so if it's all done within a system, then tracking provenance becomes much easier. In the process, they're also developing other tools. They have tools for ingesting web data as RDF using some machine learning. So you can give it a few training examples and it'll learn the structure. And in fact, this team and the court records team are actually collaborating because there are some, as you can see here, the third bullet, extracting structure from physical documents, is in fact a joint effort between these two projects. And then they're also providing some capabilities for quickly creating ontologies from data. This, if you remember, way back in the beginning, I showed you a piece of text with drugs and the drug active actions. That's an example of where the system could extract a bunch of terms for you and ask you, hey, are these related? Is there a class hierarchy here, et cetera, et cetera? And the user can tell the system what it's about, and that way the system learns quickly what the ontologies are. So it's basically human-aided thing. Again, there is a technical report available, which is pretty recent, March 2nd, that describes the system. So you can go look at it, and some of this is showing the flow of data flow of what happens when you're kind of doing the social network creation activity. And the next one is on incorporating basically geospatial information in a better way in all these knowledge graphs. So earlier we talked about GeoSPARQL. So there are some geo capabilities, but it turns out that most of the knowledge graph data that's out there is still quite handicapped in terms of its geospatial information. So here I have an example, right? If you go, you can actually go to Google and type this question: what is the distance between, I pick India and Pakistan, only because I happen to know where they are, and maybe some people don't know, so they might be wondering, what is the distance between India and Pakistan? And Google will say 1,452 kilometers. And of course, well, what is it? Because there's actually these are neighboring countries. You can do the query with US and Canada. I didn't think that was as interesting, but you get an equally surprising answer. And that's because in Google search, all of these are represented as objects with a centroid. So the lat long of the center of the centroid is what is the spatial information, and it computes distance as the distance between the centroids. So another way to say that is it's lacking adequate geospatial knowledge to be able to say, well, these are actually neighboring countries. So, what do you mean by distance between the two? Because it could be zero. And they're doing this for a variety of different domains, and actually working very actively with very different user communities. One they're working with is a commercial group that is interested in supply chain data management, and another is an NGO that's interested in ecological information. And actually, I think one is disaster-related information. It's like an international NGO. In all cases, trying to say, how do we incorporate valuable geospatial information so that data becomes much more useful with that kind of thing in it. Another thing they're doing, if some of you may be familiar with, one of the most popular sort of mapping software tools is the Esri's ArcMap. And so they're actually Esri is their partner in this project, and they're actually building the ability to ingest RDF-based geospatial information into Esri ArcMap so that the tool becomes more intelligent in terms of geospatial information. The last one I'll mention is there is this effort going on at Google called datacommons.org. As it says here, if you go to that website, it's an open knowledge repository that combines data from public data sets and then provides you tools to easily explore. So what they mean is they've actually pulled together a lot of federal socioeconomic data, like from the Census Bureau, from the Bureau of Labor Statistics, etc. And you can very easily, you should try it, and it's just very easy to just click, 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 and go through and generate these kinds of presentations, right? There are also other presentations where they draw graphs for you. In this case, there's a map and there's all this data, which is showing a lot of demographic and other socioeconomic data for a region, which was all pulled out of federal government data sets, but actually made much more easy to use and many more tools on top of it, like in this case, a mapping tool. In their other cases, they have graphing tools. So once again, showing the power of representing all this in schema.org way, RDF way of entities and relationships so that you can easily bring the data alive, right? So the data itself is being represented in these knowledge graphs, which is the whole point of these. Oh, and also, like we said earlier, remember we said schema.org is embedded in a lot of web pages, and you can see things like business hours and so on. It turns out that this data is also now being pulled into some small percentage of Google searches, which already turns out to be a lot of searches. And actually some of this information from this knowledge graph may appear in Google search because this has now been deployed and made accessible through RDF. So I think I'm ending with these. So some of the issues here are in terms that I won't cover, but you can think about it, and probably maybe some of your future lectures may cover this, is the implementation. At the end of the day, you can still get computer scientists all very agitated about how do we actually represent these things. You know, should the graphs be graphs, or should we convert them to tables? There are graph databases that have been getting better and better over the years, Neo4j, Stardog, OrientDB, and more, Allegro Graph. Of course, you can still use tabular representations, and as you all probably know, there are some really efficient processing engines for extremely large data of this type. So the triples could be simply represented as rows, and you could use Bigtable, BigQuery, Spark, whatever else might be your favorite system to go after it. And probably endless fun for computer scientists to try and shard things and optimize and so on. Another challenge, a real challenge, is actually the dynamism of this data, because knowledge graphs are about knowledge. Remember, not the epistemological knowledge, about knowledge about the data. Well, that knowledge keeps evolving because as we learn more and find out more. So what does that mean for query processing, for any inferences you might have made and so on? How does versioning work? This is a huge challenge. This is a very powerful tool, but the dynamic aspect is challenging and interesting to look at. User views are extremely important. In fact, one that has come up, and even today in 2 different meetings, this was being discussed, is how to deal with this notion of basically uncertainty, error, data quality, right? So I mentioned to you in the flood use case. If I'm a user, on my iPhone, I have a weather app, and it tells me something. It tells me what the temperature is. It tells me how much rain I can expect for the next X number of hours, and I'm happy with it. But I'm not questioning what are the error bounds on this and so on, because more or less it tells me what seems to be reasonable information. So that level of detail is sufficient for me. While how much is needed for somebody else? If someone else is doing the person is in charge of running a whole bunch of solar panels, maybe they want much more accurate information about how much cloudiness is going to be there. Or if they're scientists, like other scientists want to share my information that I'm putting out as a scientist, they might want to know even more detail. So really what you show in your knowledge graph and the amount of information that is made available depends a lot on what the user, who is the consumer of that, and what do they want to do. And here's another wonderful paper. Pascal Hitzler is one of the co-PIs of the Nowhere Graph project. And he has this paper on, basically how do you design ontologies. And some of the lessons they have learned with experience is that you need more than one domain expert with overlapping expertise and more than one ontology engineer on the team. Because like we said, these are not solitary projects that you do. These have to be done in teams. And no single person really knows everything. That's one aspect. And there are indeed viewpoints. There are points of view where two scientists might differ, because one might say, no, actually this concept is more important than that, and vice versa. So in order to get something reasonable together, you really need teams to come together. And like he says, based on our experiences, 3 types of participants are needed in order to have a team that can establish a good modular ontology. Actually, because you need somebody on the team who understands what a modular ontology is to begin with, right? You need domain experts who just know about the domain and couldn't care less that you're putting it into some formal structure called an ontology. You need ontology engineers who know that aspect of it. And you need data scientists who can actually do things with the data. They can do whatever it is, whether it's R or Jupyter or Python, or whatever needs to be done to basically munch the data and do all the acrobatics with the data. So you need that. So this is clearly a team sport, but it's essential technology for the future and has these challenges of dynamism and so on. And I think that's it. I'm going to stop there. Now I haven't looked at the Q&A in chat before. Okay. So let's see. Do you consider scientific models to count as data? Yes, or even machine learning models. Actually, some of another track in the Convergence Accelerator that we are running right now, which is in that phase 1 that I talked about, is about enabling data sharing and model sharing. And in this case, models are machine learning models. And it's really data, right? Because you're talking about training data sets, so you're trying to describe a piece of code. And at some level, you can say, well, that's all some data that I'm talking about. So in that sense, scientific models are data. Also, and there, by the way, another project actually is on, it's called MDF, Model Description Format or something like that. I'm not sure if I got it right. But they're actually looking at exchanging neuroscience models in neuroscience as data. So neuroscientists can exchange models in a consistent way. So it is data in that sense. Models are also data in the sense that like, again, if you think in terms of user personas, certain users may not care so much about the model itself. They just care about the output from the model. So output from the model, of course, is data. And as long as you tell them, so I learned that there's something called HECRAS, HECRAS. So HECRAS is a very well-known flood model for the US, okay? So if you tell somebody this comes from HECRAS, that's all they need to know. And what they need is the data, okay? So it could be data in that sense.
Yeah. So thanks, Chaitanya, for that explanation. This question is actually coming from Pat Langley, and I'll request Pat to follow up with you over email and have a conversation. If there are any students who want to ask any questions, this would be a great time. We've got about 7 minutes left before the end of the class. While we are waiting for any student questions, maybe my panelists want to ask any question. Mike or Naren, do you have any question or any comments you want to make?
So a general question, why didn't like the whole semantic web take off too much? Or did it take off in some verticals like maybe shopping or news or something where they have a little bit of structured information in the articles?
Yeah. I'm by no means an expert. There's been a lot of what do you call it? Postmortem, I guess, of that question. But what I would say is things are taking off now because of the imperative that it has to be done. One of the imperatives is this idea of heterogeneous data that needs to be pulled together. I think, and to some extent, I'm really talking about scientific data. I think I feel more comfortable talking about that. Is because not only do scientists realize that they really do need other kinds of data to be integrated as part of their analysis, but they also realize that they're doing too much work from scratch all the time. And we always say this, even in data science, that 80% of the work is just bringing the data together, but that's becoming just too much right now. People are just sick and tired of it. So I think there is now an interest in any technology that can help to make this better. That's one. So I think in some sense, I would say it's the readiness. Somehow the field was not ready. The other thing I'm speculating is it could very well be this user persona, user view thing. That is, I think you really do need to understand who's going to use this and then what is the right way to serve this data for the use cases that we are talking about. So building something that's generic without having too much of a use case, I think that might have been another of the issues with that.
All right, thank you.
Yeah.
So we have another question that is GPT-3 working as KG? I don't know if that question can even be answered because they're two different technologies.
Yeah, GPT-3, can you tell me what that is?
It's a new language model. Anyways, I think that question doesn't make a lot of sense even to me. How is NSF Convergence project handling data storage and query costs? Who is in charge of overseeing that?
That's actually an excellent question at one level because as I told you, these projects are in phase 1, phase 2. Well, the question is what happens after phase 2? Well, in phase 2, they're supposed to have built something that sustains itself in phase 3. And right now, the 5 projects I talked about are all using different strategies for doing that. Some of them are planning to start up companies to do it and therefore sell product. Others, like the court records, are very obvious, very, what should I say, vocal about that they are they're creating a non-profit, and they're not going to make any money off it. Their goal is to make all this data publicly available. So they actually have very modest costs associated with keeping it going, but they still need to find some money to cover those annual costs. So the reason I say that is how much storage and computing is needed depends on obviously what the use cases are, and of course how many users you have, right? And so these projects have to figure out that it's built into their model of sustenance that they can make the amount of money needed for the query processing and storage costs. That's the final answer. During the project itself, several of them, like the flooding project, is working with Amazon, so they're using AWS. Some of the others, the 2 projects that are creating technologies, in a sense, don't really have a platform issue because they're just really creating software. Though the social knowledge graph project that I mentioned from Mike Caffarella, I believe is a cloud-based implementation because it is in the end, it's a data sharing kind of system. Happens to have programming sort of built around it, but data has to be shared between different data scientists or programmers. So, and that's all done through the cloud. So I think eventually these are all going to be cloud-based strategies, and how they pay themselves, how they pay that cost is part of their business model.
Great, that's a good answer. So we've got like just 1 minute left. Maybe Mike, do you have any closing question or comment we can wrap up with? You're muted, Mike.
Sorry about that. Sudhir Agrawal did ask an interesting question. He says that a flip side of making data easier to use is the compromise on people's privacy. And he's wondering whether the knowledge graph efforts have been looking into ways of dealing with that or helping in any way to control data usage.
Actually, again, excellent question. So the first open knowledge network workshop we had back that I showed you the report, I have to say that one of the original people who, I was at NSF at that time, and I've come back to NSF, but one of the people with whom I worked and who instigated this is actually Andrew Moore, who used to be at CMU, is now at Google again. And one thing we decided right off the bat, the first thing we said in the meeting is no private data in this open knowledge network. This is scientific data, and we are not going to deal with the privacy issues, exactly for the reason that, wow, that's such a huge problem, right? So all the examples I gave you, even the biomedicine problem, is actually biomedical information. There's no patient information there. And actually, one of their use cases, I didn't talk about it, one of their business model use cases is to connect their knowledge graph to an EHR graph and then do medical, and medical, that's the precision medicine aspect of it. But the graph itself is actually public open sourced data. So this project has sidestepped the issue by saying no private data. Having said that, I want to just mention to you a couple of things. One, because Stanford may actually be part of it. So because we have just been talking with the US Census Bureau. So the US Census Bureau, as you know, has all sorts of micro data about all of us. And they have all sorts of micro data about businesses in the country, all the details, right? You can actually get access to that through a protected system called the FSRDCs, Federal Statistical Research and Research Data Centers. And specific universities are part of it. So the basic answer to that is the way, if you did have private data is protected access, that's one way you do it. And FSRDC data, and we are talking to them about how do we get people, as you can imagine, some of our projects are very interested in getting access to microdata. So how would you connect an open knowledge graph to another one that has private data is something we're looking at. The other thing I'll say is NSF, just recently we announced we're running a workshop in a couple of months called on national secure data sharing system. So how do we create a national system to securely share data, and which might include some of this BII. And by the way, track D that I talked about, which is about data sharing and model sharing, explicitly includes sensitive private data, because people do want to share private data, as long as you have the authority to do it, access control and all of that, or they might anonymize it. And so as NSF, we need to solve that problem. How do you actually share private data? But in the OKN, the statement is it's all about free open scientific data.
Okay. Well, I wish we had more time for discussion, but unfortunately we are at the end of the class time and we have to conclude. So Chaitanya, this was a fantastic presentation. You gave us an overview of some really fascinating and interesting project, and probably your presentation has raised a lot of questions, which has at least left me thinking about a lot of follow-ons or follow-ups to this. So with that, I'd like to thank everybody who is in the webinar, and I look forward to continuing our seminar next week. Next week's topic is going to be on what are some of the data models used in knowledge graphs. All right.
Thanks very much.
Thank you, Chaitanya.